Hi everyone. A very good afternoon to all of you. I am from the TileLink team of the Two-Chip Solutions and welcome you all to this webinar. Today we are going to present a webinar on TileLink. Our agenda of this webinar is to provide a tiling overview along with the architecture of tiling, followed by the bus utilization process. Then we'll explain the operations supported by the tiling and what are the different operations and the message types supported at the different conformance levels. That is the TLUL, TLUH and the tiling cache with a small overview of cache. At the end, we'll provide the overview of the two-chip tiling VIP features and the advantages. Basically, TileLink is a chip-scalable interconnect standard used for connecting the multiple masters and the multiple slaves, maintaining coherent memory in all the masters. It is used in the SoC to connect the general-purpose multiprocessor, coprocessor, and many complex devices, providing a low latency and a high throughput transfers. Tiling can be implemented over a scalable, hierarchy composable, and a point-to-point networks. It is a cache coherent protocol supporting a MOESI equivalent protocol, which is a full cache coherent protocol that have all the possible states commonly used in a cache protocols. Now the TileLink, as I said, have three conformance levels. As you can see, we have TLUL, TLUH, and the TileLink C. Here, the TLUL is used for connecting the low bandwidth peripherals. It performs the basic read and the write operations only. The TLUH, other than the read and the write operations, it also performs the bus operations, atomic, and the hint operations. Finally, we have the tiling cache, which adds three additional cache transfers. That is the acquire, probe, and release, which uses all the channels from A to E. Now, we'll see the architecture. This is the TileLink architecture. Here, you can see in the figure, the agents are connected through a link. The TileLink agent sends and receives messages or perform the operations over a point-to-point channels within a link. The TileLink protocol defines 5 independent channels over which message can be sent by the agents. In the table here shown the direction of each channel along with the purpose. The channel A, C, and E are the sends the messages from the master to the slave, and the channel B and D are used to send the request and the response messages from slave to master. The TLUL and TLUH operations will be performed on the channel A and D only. So these are the mandatory channels. The TileLink C adds 3 new channels, that is B, C, and E, in order to perform the cache operations. In order to avoid the deadlock, the TileLink has specified the priorities among all these channels in an increasing order. Just like channel C is having the higher priority than the channel A and B. So we can see the channel E has the highest priority than all the other channels. The TileLink supports a wide variety of network topologies. As you can see, there are 2 modules, a crossbar and a cache. Have the agents that have the master interface on their right side and a slave interface on their left side. So when we having multiple master connected to multiple slaves, we'll be using the crossbar in between the masters and the slaves. So TileLink is a synchronous bus protocol. Both the master and the slave interface on the TileLink must share a same clock, reset, and power. Here, every signal will be sampled on the posage of the clock. Reset is active high and must be applied for 100 clocks, as valid must be driven low for at least 100 clocks when the reset is asserted. It is forbidden for the one side of the TileLink to power down while its opposite is powered on. To avoid this, we can place an adapter in between. Now, all the channels are implemented are unidirectional parallel bus. Each has a sender and a receiver. Many TileLink messages contains a data payload depending on the size of the message and the bus. And it need to be spread out across the multiple clocks as a beat. Any operation is regulated by the exchange of beat between the agents on a particular channels. For the correct implementation of the bus serialization of the ready and the valid signals, the flow control rules must be followed. So here in the flow control rules, the sender will raise the valid to offer the availability of a beat on a channel, and the receiver will raise the ready signal to indicate their ability to accept a beat. When the receiver are busy, it will not raise a ready signal and will not accept a beat. Only when both the ready and valid are raised concurrently, then the content will be accepted and the beat is exchanged. Here are the rules. If a ready is low, the receiver must process the beat. If a valid is low from the master, the receiver must not accept the control and the data signal to be syntactically correct TileLink beat. A valid signal must never depend on the ready. As a consequence, there must be no combinational path from ready to valid for any of the control and the data signal. A receiver may hold ready low in accordance with the deadlock freedom rules. There are few additional restrictions for the channels which carry a burst. Now, what is a burst? A burst is said to be in progress after the first beat has been accepted until the last beat has been accepted. When a burst is in progress, if valid is high, the sender must additionally present the following things. The sender must present only the beat from the same burst. It should present the control signals identical to those of the first beat, and all the data signal corresponding to the previous beat address plus the data bus width in the byte. It should also present the final signals changing only once within each burst. So all these are the flow control rules which must be followed in the TileLink. Just remembering these rules, here is an example for a ready and a valid handshaking. Here, there are 6 messages which are sent from one agent to the another. That is F, G, H, I, and J. As I said before, a beat is always exchanged only when both the ready and valid are high. So we can observe in the figure for the beat F0, the transfer didn't happen for the first clock, as the ready is low and the valid is high. So the transfer happened on the second clock cycle only when both the ready and valid are high. If you observe for the F2 beat, in this case both the ready and valid are high, so the beat will be transfer operation on the same clock. Also, this F burst has followed the additional rule of the burst, like the control signals of the beat are identical to those of the first beat. Deadlock freedom. So a TileLink is designed to be a deadlock free by construction. In order to avoid the deadlock, we specify 2 sets of rules to which a conforming system must adhere. Rule 1. Allowable topology of a TileLink network. The structure of the agents and the links must be a direct acyclic agent graph. Here you can see a direct acyclic graph following the rule of a deadlock freedom. You can see there is a no loopback link between any of the agents, like from slave to master or any of the crossbar. The second rule to follow the deadlock freedom is govern the condition under which a receiving agent may reject a beat of a message while lowering a ready. To avoid a deadlock, every request must eventually be answered with a response message. And response message always has the higher priority than the request message. The four reasons an agent may reject a valid beat by lowering a ready are: first, a receiver may choose to enter a bounded busy period during which it will never raise a ready. Second, when a response to a request received on a channel is being rejected, the responding agent may lower a ready of all the channel with a priority less than or equal to that particular channel. Similarly, while a recursive message following a request message from a channel X is rejected and a response message sent on channel X is not received, the receiver may lower a ready of all the channel with the priority less than or equals to X. There are few more rules for request and message ordering. Okay, the three rules for the request message ordering are: the first bit of the response message presented on the response channel on the same cycle that the first bit of the request message is presented, but not before. The first bit of response presented on response channel before all the beats of the burst request message have been accepted, or after an arbitrary delay. So we can observe the first request message, that is get message sent from the channel A, has received the access act data response from the D channel after an arbitrary delay. And the second request message from the channel A has received the request message on the same clock as per the rule 1. The burst request and response. Here in the waveform for the burst operation, the first beat of the response message is presented no earlier than the first beat of the request message. So satisfying the first rule of the forward progress rules. In the waveform, the master is processing an atomic operation. Here the request message and the response message both carry the data, and as per the size and the bus width, 2 beats of the request and response are transferred. As we can see in the waveform, the first beat is accepted on the same cycle of the request is accepted. For the second request beat, the valid goes low for 1 clock cycle. According to the rule, the ready of the response channel must also be low. Otherwise, it will be violated that response can never be presented before the request is accepted. The second beat will be completed at the third clock, where both the request and response are accepted at the same clock. Now there are few errors. There are 2 types of error which we may receive while transferring a message request. The first is corrupt data error. Second, access denied error. The corrupt signal is presented on all channels that carry the data. Any beat in the burst can get corrupted. Access denied is a single bit control signal that indicate whenever an attempt, access or permission transfer operations are processed by the receipt or not. When an operation is denied, it must have no effect on the permission of data block, nor change its content, nor trigger any side effect related to accessing the data. Now, the TileLink operations can be categorized in 3 groups: access, hint, and transfer. Here the dotted arrows, as you can see in the diagram, indicates the request and response message pair. The TL conformance only requires supporting the get and the put access operations. TLUH requires all the hint and the access operations. The TLC requires all the transfer operations. Moving forward, this table displays all the TileLink messages along with their operation type and what type of response is generated by the particular message. Also, you can see based upon the channels, all the messages are categorized with their opcode value that is used to identify them on the TileLink bus. We'll go through these messages later in the slides. Operation ordering. In operation ordering, it is not necessary the operation will complete in the order they are issued. They can complete in any order. As we can see in the waveform, the response can be arrived in any manner of the request. Operation do not necessarily receive response in order. As in the waveform, the operation are generated as 1, 2, and 3 and completed the response as 3, 1, and 2. In the TileLink network, there may be multiple outstanding operations in flight at a given time. These operations may complete in any order. Response issuing agents are responsible for ensuring that there is a valid serialization of the operation received. Starting with the first conformance, TileLink uncached lightweight. This is the first TileLink conformance level. The TLUL is used for connecting low bandwidth peripherals. TLUL performs memory access operations, that is, the get and the put operation. The get is used to read some amount of data from the backing memory, and put operation writes some amount of data to the backing memory. We can also perform the partial write where some of the bytes are masked. So these are the message. On the left, you have a put full data and a put partial data message, which will be sent by the master and will receive a access ACK response from the slave. This is just a simple request response operation. Similarly, there is a get is request message sent from the master on channel A to perform read operation. Then we'll receive a access ACK data response from the slave on the channel D. Here are few more details on the TLUL messages. Get is used to read a particular block of data. Put full data and put partial data are used to write the data block. Access ACK is a dataless response for the put full and a put partial messages. Access ACK data is a response message for get message that contains the data. Moving forward with the TileLink uncached heavyweight. TLUH builds on the TLUL and provide 3 additional operations. That is the atomic, hint, and the burst operations. Atomic operations access memory and perform the arithmetic and the logical operation to change the value of the data in the memory. The hint operations performs on future operations. The burst messages allow operations to target larger address range and specifically enable message with data size bigger than the width of the physical data bus. Now we'll go through the message flow of the TLUH. As you can see, we have added the arithmetic data, logical data, and the hint messages on the channel A. So for the atomic message request, that is the arithmetic and the logical, will receive the access ACK data as a response, and for the hint message, we'll receive the hint ACK response message from the channel C. Here we can see a more detail on these messages. Here the arithmetic data and the logical data message is a request made by an agent that would like to access a particular block of data in order to read, modify, write it by applying a arithmetic or a bitwise logical data operation. Here both these atomic operations send a request message with some data block, then access a particular block of data and perform the operation between them, and store the modified data back into the memory. The intent is a request made by an agent that would like to signal its future intention to access a particular block of data. It is future intention sent by the master to access a particular block of data. This operation doesn't affect the performance of protocol. A hint tag serves as an acknowledgement message for the hint operation. The burst messages can contain the data larger than the width of the physical data bus. The subset of data that can be sent over a link in a single cycle is called a beat. The burst message can be any of the various messages within a get, put, or the atomic operation that contain the data in their name. Now, before starting the TileLink cache, we'll go through some basic concept of the cache. What is a cache? A cache is a place for hiding and storing things. As you can see in the figure, we can place a cache block in between a CPU and the main memory block. Okay, so cache contains a copy of portion of main memory. When CPU attempts to read or write a word, cache is checked first. If found, it is presented. Otherwise, a line of word is brought from the main memory to the cache. Two terms are used to categorize the cache efficiency of a program: a cache hit rate and a cache miss rate. When a cache is checked, the address of the cache line is present, then it is called a cache hit. And when a cache is checked, then a particular address or a cache line is not present, then it's a cache miss. The hit rate can be calculated by a cache hit by the memory request into 100. And the rate can be measured in write, read, or both. A TileLink cache completes the TileLink, and it's a third conformance level that uses all the channels. A TileLink cache, the master agent has the capability to cache the copy of block of shared data, and these local copy must be kept in coherent according to the implementation defined policy. In total, TLC adds TileLink protocol specification, 3 new operations, 3 new channels, and a 5-step message sequence template, and 10 new message types. The new operations are transfer operations that create or remove cache copies of data blocks. A transfer operation never modifies the value of the data, but rather transfer the read and write permissions available to the copy of them. As mentioned, the TLC adds 3 new channels to support the transfer operations and perform the memory access operations. The 5 channels used by the transfer operations are channel A, B, C, D, and E. The channel A is used by the master to initiate the acquiring permission to read and write a copy of cache block. Channel B is used by the slave to query or modify a master permission on a cache block. Channel C is again used by the master to acknowledge a channel B message and also used to release a permission of the data block along with the dirty data. The channel D is used by the slave providing the data of the permission to the original requester, guaranteeing the access of the cache block. Channel E A master provides the final acknowledgement of the transaction completion used by the slave for the transaction serialization on the channel E. The three new operations added in the TLC are termed as the transfer operation because they transfer a copy of block of data to a new location in the memory hierarchy. The three operations are the acquire, release, and probe. Acquire, create a new copy of a block or change the particular permission of a block in a requesting master. Release relinquishes a copy of block or change its particular permission of block back to the slave from the requesting master. Probe forcefully remove a copy of block or permission from a master to a requesting slave. Now we see the message flow of TileLink cache. This is the complete message flow of the TileLink. Here we have added more messages like acquire block, acquire param, probe, release, and many more. So we can see the acquire block and the acquire param message are generated on the channel A, and the response grant and grant data will be generated on the channel D, and the grant act response will be driven on channel E for the grant or the grant data messages. Similarly, probe request is generated on channel B from the slave, and the response probe ACK and the probe ACK data is received on the channel E from the master. And the release message uses the channel C and the channel D for the request response. Now we go through all the messages in brief. Starting from the acquire block is used by the master to obtain a copy of block of data that it planned to cache locally, and it can also be used to update the permission of the block that is already in possession. The acquire param is used only to update the permission on a block which is already in possession. Grant and grant data are the response messages of the acquire. Grant data is used to provide the copy of data block along with the permission using the cap permission type, and grant used to provide the permission access only to the cache block. Grant ACK response message is used by the master agent to provide a final acknowledgement to the transaction completion. Moving forward with the probe messages. A probe block is used by the slave agent to query or modify the permission of a cache copy of a block stored by a particular master agent. A probe param is same as above probe block, but probe param must only be used in situation where a no copy of data is required to complete the operation. A probe ACK and a probe ACK data are the response messages used by a master to acknowledge the receipt of a probe. Along with the probe ACK data will write back a dirty data that the requesting slave agent required, and both using the shrink or a report permission type based upon the scenarios. Moving forward with the release messages, release and the release data are used by the master to voluntarily downgrade its permission on a cache block using the shrink or the report permissions. The release data will also write back the dirty data to the managing slave agent. Release ACK is used by the slave agent to acknowledge the receipt of the release and the release data, and in turn used to ensure the global serialization of the operation by the slave agent. So all these are the messages of the TileLink cache. Moving forward to the advantages of the TileLink. First, it decouples message protocol from the wire protocol. The TileLink is designed for the RISC-V requirements, that is a simpler design with the following features. It reduces message protocol risk, assume all connected hardware is trusted, and only power of 2 block transfers are possible. Master-slave point-to-point protocol. A TileLink is also provides a out-of-order design with optional ordering. Cache coherent memory block motion is supported, and tiling is designed for composability and a deadlock free. Now a question arises why we should go with the tiling, as many other bus protocols are still present. As you can see in this table, there are few features that distinguishes the tiling and the other protocols like the AHP, AXI, ACE, CHI, and the Wishbone. The points to distinguish are the open standard, easy to implement, cache block motion, multi-cache layer, reusable off-chip, and the high performance. You can see every protocols are lacking at some point, mostly lacking in the cache and easy to implement. Some lack in the performance and the open standard also, but the tiling are fulfilling all these needs, so making it a preferred protocol. Now talking about the TrueChip TileLink VIP, we can configure the VIP in two modes. One, a single master and a single slave. Other is multi-master and multiple slave using a crossbar. In this mode, there is a single master, single slave connected with a TileLink interface on which a TileLink monitor and a TileLink scoreboard is mounted, performing the protocol and the data integrity check. As per the requirement, user can replace the master or slave or both of them with a duty. As user can create multiple environment as per their requirement. Moving forward, we have the multi-master and multi-slave using the crossbar architecture. In this mode, multiple master and multiple slaves are connected using a crossbar. Any number of master and slaves are possible. As per the requirement, all the masters and the slaves can be switched with a duty. The crossbar can replace with the duty in case a crossbar monitor and the scoreboard can be plugged in as a crossbar checker. All the master and the slaves and the crossbar can be replaced with the duty, and the complete VIP will work as a passive monitor. As per the requirement of the multiple crossbar in a system, the multiple environment instances are also possible. Now we go through the features of the TrueChip TileLink VIP. The VIP supports all the 3 conformance levels and all the type of operation supported on the 5 channels. The VIP follows the acyclic agent graph and support any tiling crossbar matrices. The data, address, source, sink, and the size width can be parameterized. The VIP provides user configurable memory map for different type of memory regions. All transfer can be configured with the user defined values. VIP also support for the busy and a wait state using a weighted constraints. User support for outstanding transfer and also support all node in a coherency tree. All type of permission transitions are also supported. Support different restrictions along with their checks in the VIP. The TrueChip VIP also provides a wide range of programmable protocol checks along with the bus assertions for all the protocol scenarios. The callback functionality is also supported in the components like master, slave, monitor, and the scoreboard. The VIP provide the bus and a configuration coverage and also the assertion coverage and achieve 100% in all the simulators. The VIP supports use of randomization and the constraint to generate the corner scenarios. Support for the dynamic configuration is available. Component can be configured on the fly for each new packet. Also provide support for the UVM register model and can generate the sequences in RAL format. VIPs support a module-based wrapper, making an effortless integration. Message management, error or the warning reporting can be controlled by changing the severity level or by suppressing it. Every error or the warning have a unique error ID which will provide a detailed description of the error, which is helpful in debugging. VIP provides the summary of all the transactions received on the bus along with the real-time bus transaction detail in the log file. The VIP supports for a TrueEye GUI for easy debugging like a real-time transactions, latencies, statistics, and many more. All this will be available in a tabular and a graphical format. Now we'll learn more about the TrueEye in detail. A TrueChip comes up with a TrueEye, the debugging tool. The TrueEye helps in easy integration that will reduce man efforts and time, help in easy and effective debugging and searching features. It also easy to detect and correct the errors, also easy to configure. Here you can see a table view of a easy debugging. For a easy debugging, a table view divided into two parts, a transaction and a transaction details. In the transactions, there are multiple columns that will display on the transaction happened on the interface. On the top, we have a search option. Okay, in order to search any particular address or opcode or any other column value in the entire simulation. Transaction detail will provide much more detail of the selected transaction. In the bottom corner, we have a error count that will display the total error counts in the entire simulation. And using these arrows, you can directly jump on the errors. This table view is one of the features of easy debugging. There are a lot more features of TrueEye you can contact for a live demo. Moving forward, these are the TrueChip TileLink VIP deliverables. All the VIP components like master slave, monitor, and scoreboard are provided along with the different type of test suits like the directed, random, error injection, and dynamic test suits. In the documentation, we'll provide the integration guide for easy debugging and integration along with the user manual and the release notes. So this is all about the tiling. Thank to all of you for joining.